Good afternoon and welcome to today's BioExcel webinar, the next one in our BioExcel webinar series. This is actually effectively the first of a two-parter. There'll be another webinar next week on a related subject as well. In particular, it's on accessing cloud and HTC resources in BioExcel. So I hope you can make it along to that one as well. So my name is Adam Carter. I'm in the BioExcel project, and I'm going to give a very quick introduction to the BioExcel project and what our centre is about. That'll take no more than 5 minutes at the most, and then I'm going to hand over to our presenter, Lee Larkham, who's going to give today's presentation. This is just to warn you that today's webinar is being recorded, so you will be able to find the recording on YouTube and on the BioExcel website after today if there's something you want to look at again, and you should also be aware that that includes the question and answer session at the end. So for those of you who are less familiar with BioExcel, this is just one slide that I'll use to introduce some of the things that we're doing in the Centre of Excellence. There are sort of three pillars to what we're trying to do in our Centre of Excellence. The first one is to support biomolecular software, and in particular to improve the performance and efficiency and scalability of some key codes in the area of computational biomolecular research. In particular, we have GROMACS, HADOC, and CPMD, and we have some of the lead developers of some of these software packages actually in the project. So part of the work we do is to make some improvements to these important codes. But as well as the codes themselves, another important part of what we're trying to do is to promote excellence in usability. So we're trying to make it easier to use these codes as part of a wider workflow or pipeline. So one of the things that we're doing in the project is to devise efficient workflow environments which also have data integration involved in them as well. And you can see on the slide some of the platforms that we're looking at in the project. And the last part is important to us, is that we want to be involved in consultancy and training activities. We want to be promoting best practice and training end users. The webinars are part of our plan for doing this. There's also training courses that we run, and as I'll mention in a moment, interest groups. So you can find out more about those on our website. So these are the interest groups that we currently have running in the project. You'll see that some of them are subject area focused on things like integrative modeling, free energy calculations. Others are more based on a particular group of people, like people involved in industry or entry-level users who are people who are not so familiar with biomolecular simulation but who are getting involved. So if you're interested in any of these things, you can sign up to any of the interest groups on the project website. So just to let you know that there will be time at the end of this webinar to ask questions, and we would encourage you to do so. So if you have any questions, you can type them in using the question tool in GoToWebinar. Hopefully you'll be able to see on your control panel. It might look a little bit different to this, but you should see a questions section where you can enter any questions that you have. And then at the end of the webinar, I'll either invite you to open your microphone to ask your question directly to Lee, or if you don't have a microphone or you prefer to remain silent, I can read out the question on your behalf so that Lee can respond. So now I can introduce today's presenter. Lee Larkham began his scientific career in the lab with an undergrad degree in genetics from Queen Margaret University in London, and later a PhD studying Chlamydia trachomatis at Cranfield University, where he stayed and worked himself up to the post of lecturer in genetics and computational biology, and he was the course director for the university's MSc in applied bioinformatics. And then he moved to industry, first as bioinformatics lead for Lonza Biologics, and then more recently as an independent consultant. So his focus has focused mainly on functional genomics and data integration for the study of oncology and the discovery of novel biomarkers and targets. He's currently Elixir UK's training coordinator for research science, based at the MRC Human Genetics Unit at the Institute of Genetics and Molecular Medicine at the University of Edinburgh with Professor Chris Ponting. So it gives me great pleasure to welcome Lee to give today's talk. So I'm now going to hand over to Lee and invite him to take control. So I will now make Lee the presenter, and Lee, you can take it from here. Thank you.
Thank you for the introduction, Adam. Hopefully you can all see my slides now. That seemed to go smoothly, which is a good start for a webinar, the presenter handover. So, as Adam said, I have a background pretty much across both academia and industry, but the important thing with that and for this webinar is that in both cases I've had to work out how to give my team the right computing resources they need to do their work. And in the main, that work has been bioinformatics and bioinformatics related things. So most of the stuff I'll talk about today is bioinformatics related. So sorry if you're not a bioinformatician, but actually in many cases in technical research science where computers are involved, I think a lot of the examples or lessons I learned that I'm going to share today are probably applicable no matter what the actual subject is. So hopefully there'll be something for you to take away and it will be helpful. Really what I want to do in this short presentation is to give you some idea of options and possibilities and ways to maybe approach this, and really to help you decide what your requirements truly are for getting compute resources for your team. And of course then you can decide whether anything I say in here is useful to you or whether next week's webinar is more of value, which looks at even more high performance computing than I will talk about in this one. I think where we're starting from with this is a metaphor sort of summed up by this picture. You've probably got some computing, you may have had it a long time, you may find it doesn't work for you, it may be dusty, your skills might be rusty, your staff may not be able to use what you've got, and there's lots of considerations there about how your team should be properly resourced or expanded to try and meet what are probably grander computational needs than you've had in the past. There's a few things you need to think about right at the very beginning before you're going to go from that dusty old machine on the previous page to something new and shiny. I think the first thing to think about is actually not the computational problem, but to think about the people that you have. So you've probably got some scientific questions, you've read papers where people are doing amazing things that you can't do, but do you actually have the people with the skills? And I would argue that one of the first things to do is to look at not so much what you have in terms of computing, but who you have, who you maybe need. Should you be recruiting a person before you buy computers? Should you be looking for someone to collaborate with who maybe in some cases has the computers you need and the skills? So I would have to sort of recommend the first thing to do when thinking about your compute requirements is to actually think about the people requirements first. But once you get beyond that and you realize you do need to do something in your team, the most important thing is probably going to be a huge sackload of money. Doesn't have to be euros. I just found a nice picture of euros. They're worth more than they were to us in the UK at least. But the one point I would like to make perhaps is that you don't need perhaps as big a stack of money as you might initially think. So part of the message in this talk maybe is to think about what you can do with actually quite minimal investment in computing, and maybe that will serve your needs before you go and spend out on something very flashy with lots of lights and makes lots of noise, but actually is more than you need. So I would like to take a very pragmatic approach to considering what you need in terms of compute resources. Chances are you will decide that you need to buy a computer or maybe repurpose one that you've got lying around. At some point, you're probably going to have to talk to your IT department. And I put this slide in really because of many years now of frustrations of working with IT departments as a computing-related scientist. You probably have to speak to your IT department, but it may not actually be the best way to go forward with your compute resource requirements, but you just might not have any choice. So here I'm talking about those kind of scenarios where you find that you have to buy a new computer, but your university or your company has a preferred supplier. All computing is purchased through the IT department. They specify the machines, they tell you what they recommend, and it becomes very difficult as the scientist to make the case that you can specify what you or your staff need, even though you're doing this for scientific reasons and you maybe have absolute requirements. I have often found that having to work through a traditional IT department throws up all kinds of blockages along the way. You will occasionally find people who are fantastically helpful, but other times you'll bump up against process and procedure that makes this a very frustrating exercise. All too often, the scientists will be specified the same kind of computers as the receptionist will have because they buy them in bulk. And you can do some science on those, and you can, in my case, do bioinformatics on them, but it's difficult to then justify why you need a £2,000 workstation when they normally buy £200 desktops. So you're going to have a conversation with the IT department, but maybe you need to think a little bit about what your expectations of these people are going to be. So I have some sort of do not caveats on this slide. When you approach this conversation, I think do not expect them to understand your scientific requirements of the computing. You've got to try and be able to make that case that you need something different, but they're not likely to understand exactly why, and that makes it a very difficult discussion. Do not expect them to install all your scientific software for you. They'll be used to installing Microsoft Office, etc. But if you want something done that's a little bit more fancy than that, or a little bit more off the wall, then they're not necessarily going to want, in many cases, to dedicate the time to somebody doing that. Don't expect them to offer you end user support. If you can't install MATLAB on your machine, then they're not necessarily going to come and do it for you. They're certainly not going to tell you how to use it. So I think if you go in with sensible expectations, you can have a good dialogue with IT departments, but be aware that they often have restraints on them about what they're supposed to be doing, and you've got to try and find a way to work with them around those restraints, possibly in a new way that your organization hasn't had to do before. And one of the things that makes that easier is to try and make the argument that you're not actually making an IT purchase, you're making a purchase of scientific equipment. And this can still be a bit of a challenge because at the end of the day it is a computer and it may well fall to your IT department. But in some companies and certainly in universities, IT equipment is purchased through different routes to what you might buy a PCR machine or a sequencing machine or a piece of scientific equipment. So you need to approach this as a scientific equipment purchase and try and fight that case. It's not always an easy one, but that would be my recommendation. So try and avoid the special purchasing arrangements that your organization has for buying computers. Try and tackle this as scientific equipment. You will probably have a fight, so be prepared. But at the end of the day, I've always managed to do this. It has been frustrating. But once you've made the case, everything in the future becomes easier. It's worth persevering with. Once you've done this once, you'll always be able to do it again. Okay. So when you're going to buy your new computers, you're going to hopefully be thinking about what you need to do with them. And we'll come to some ideas of what you can do with different types of easily purchasable computers in a minute. One thing I'd like to flag up early is to think about your data transfer, data storage requirements. Depending on what science you're trying to do with your computers, and in my case in bioinformatics, we can have some quite large data sets, quite large data requirements. You may well be doing something which is completely different to the rest of your organization. So in my little biog there, you see I worked for Cranfield. At the time I worked for Cranfield, we had, managed by central IT, about 36 terabytes of user space storage for people's emails and documents and whatnot. And the HPC cluster had 36 terabytes of its own, which was reasonably impressive at the time, and I was there a little while, and we're going back a few years. But you can very easily be doing something in either computing or high-performance computing, which is far in excess of the kind of storage and data requirements that have been considered by your organization before, when they're only thinking about desktop-level computing. You will probably have to have plenty of local storage, make sure you've got backups, make sure you're looking after your own data. Now, the other thing you need to think about is what you're connecting these machines to. I put a little red calculation at the bottom of this slide. It's not unusual to have to get hold of anywhere up to 1 terabyte of data in bioinformatics. And if you're connected to a standard 100 meg per second Ethernet network, that's going to take a long time to move from wherever it is to your machine. And we're not even considering here the fact that it might be off-site somewhere else. If you've got data in your lab and you need to get it to your desk, this is a kind of typical scenario. It will be easier to put that on a hard drive, pick it up, carry it to the other location, and plug it in there. But it's not something that's difficult to get around, but it is something you need to think about. I also mentioned here you might need to look into options like RAID, which is somewhat technical, but gives you options for how you can string disks together in your workstation, maybe to give you slightly faster disk access, maybe to give you redundancy if you've got valuable data. I'm not going to go into too many details on that, but if you think you need large amounts of data, you need to look at that storage in quite an amount of detail, and that's probably where you can get some local advice from IT people, even though they're not necessarily going to support you in it. They will have the knowledge that you can sort of pick their brains and understand maybe what you need to do. This slide is a little bit more of a personal view. I'm going to talk a little bit about platform considerations. 3 main platforms that most people will talk about on your machine, on your desktop: Windows, Mac OS, and Linux. And this is slightly polarizing sometimes. People have their favorites. People advocate for one or the other. If you speak to a Windows person, then Windows is the best. If you speak to a Mac person, then Mac is the best. If you speak to a Linux person, Linux is the best. To be completely honest, they are all as good as each other, and it depends on what you actually have to work with in your organization. If you've got Windows support guys in your company, then trying to deploy a Linux machine or a Mac in your office is going to be much more of a fight than a Windows machine. I'm presenting today, sat in a room at the EBI, and you're hard pushed to find people in the EBI who aren't using a Mac, and they support Macs very well. But do you really need to choose one or the other for your computing needs from a technical point of view? And I would argue that in many cases now, you actually don't. In scientific computing, particularly in bioinformatics, there's a legacy of software written for Linux, lots of open source, well-established, important tools and such like written for Linux that run on the command line. And the benefit over the last few years of using macOS in bioinformatics has been to have a good user desktop where you can run something nice like Microsoft Office in your corporate or institutional environment, and at the same time drop down to a Unix shell underneath and run the same command line tools you would be using if you were using Linux. Windows has been a little bit more limiting in that regard, although as of last year's update, you can now run a Microsoft-supported Linux distribution underneath as a subsystem in Windows, which provides you access to run pretty much most of the Linux commands and Linux tools that you would have wanted to do, in the bioinformatics world at least, on Linux or macOS in the past. So the lines between these are blurring to the point where I would suggest now whether you might use one or the other comes down to personal preference more than a technical necessity. Of course, always check that your software would run on one or the other. But in many cases where we would have argued in the past that you need a machine that's running some form of Unix shell to log into remote machines or do the tasks that you need to do, actually all three of these are pretty equivalent in that regard now. So don't get too hung up because all your bioinformatics friends use macOS. If you don't want to and it doesn't suit you, then you don't need to. Incidentally, I was a Mac user, now I'm a Windows user, purely for the reason of that Linux subsystem. So I've got a few slides now with some example machines on, and I think I need to make it clear that I'm in no way advocating the purchase of any of these machines. I'm not supporting HP with this slide. I just happen to grab a screenshot of a laptop with a price and a specification so we can talk a little bit about that. So what I wanted to do, and I've got sort of 3 slides like this, is just show an example of a machine and then talk about a few of the things from a bioinformatics point of view at least that we can try and do on that to give you an idea of what maybe is possible or isn't possible before you go out and think you need £1 million grant to do some HPC. So on a standard laptop or desktop in this price range, this is a £400 basic laptop that actually your IT department is probably buying on a daily basis. We've got something here running Windows 10, which, as I say, you can now run some Linux stuff on there. You can remote desktop into other machines quite easily, and you can run local tools quite nicely. It's got a reasonable processor. This one, in fact, even as a laptop, has what I would consider to be quite a large amount of memory, 8 gig of RAM, and a terabyte of storage. This kind of thing just was not heard of 5 years ago. So what you've got here is probably something which is pushing what you would have had to buy a higher performance workstation 4 or 5 years ago, and now you can pick up relatively cheap. So it does do an awful lot of things that in terms of running off-the-shelf software and basic computational tools. There's a few examples in the bioinformatics world. With a laptop like that, we can use all kinds of web-based tools and repositories, access all the data we would ever need, store quite a lot of it locally. We can do basic coding and do pipelining and scripting. Perl, Python, and R being the bread and butter of this community particularly. And it can always be a window to another more powerful system. So if you are using either higher performance workstations or some proper HPC, getting shell access or remote desktop access to these things, the power is on the other system. This machine will easily be your window into that. But if you do have slightly greater needs, and normally I would suggest that this need comes in terms of your data visualization, and in my experience, mainly when doing things like molecular modeling, you need something which has a little bit more power behind it, certainly better graphics. We're now in sort of workstation class. Here we're talking about something which is up near the £2,000 including taxes mark. But this, it's an expensive machine, certainly in terms of what your IT department will be buying as standard desktops. So you're starting to have to make that argument of why you need to spend another £1,500 on a machine than everyone else in your department maybe, and you're going to have to start making those scientific arguments as to why that's important. But with something like this, you can do pretty much all of the molecular modeling you might want to do, apart from really good molecular dynamics simulations maybe for a long time. But the molecular visualizations and graphic stuff would be great on here. This machine at that price has got probably anywhere between 8, 12, maybe 16 cores of processor in it and a decent amount of memory. So we're a step up from the previous example. And so you can do a little bit more, I'm suggesting on this slide. In the bioinformatics world, we'd be looking at buying something like this to do some genome analysis, some molecular simulations, easily doing things like docking, perhaps not so much the dynamics, but metagenomics, fine in a limited way, some genome assemblies. It's a good machine. In my office, I have a laptop like the last example, and I have one of these when I need to do these tasks. But there's always a temptation to look at something bigger, and I picked this example. They're harder to find examples of these desktop class machines around, but they are there. This is arguably not too expensive in terms of the performance you will get from it, but it is a big ask of an IT department to be stumping up, in this case, nearly $50,000 to get a machine like this. I think we are well into that realm of justifying this as a special purchase in that scientific equipment area. But if you look a little bit at the specification on here, we've got quite a lot of computer cores, we've got a lot more memory. This kind of thing will do next generation sequence analysis quite nicely. You'd get some decent small protein size molecular dynamics simulations out of this. So if you're going to be doing those kind of things as bread and butter in the lab, this is a cheap option in some respects compared to if you're going to be doing sequence analysis compared to the sequencing machine. This is certainly a cheap option, but it is a step up, a step change from the last example. But these kind of things are relatively easy to acquire, not too expensive, but you can do an awful lot on something like this. But before you go out and stump up $50,000 on a almost desktop supercomputer, we'll say, I think you should sit down and think about what really is the bottleneck in your research and why you can't do what you want to do on the laptop example I gave you, or the workstation example. And then, do you really want to support a machine yourself, or is it time to collaborate? Is it time to go and look at compute resources that other people have and you can make use of through and use their expertise? So what really is that bottleneck to your research? Have you got actually quite a simple job to do? And many bioinformatics tasks are relatively simple, but they're a simple task done on lots of data. So actually, what you're struggling with is getting the data to your machine, storing it locally, accessing it quick enough. The data bottleneck can be from the storage, not necessarily from the processor. There you might be better off with a new machine that has faster drives, RAID arrays, that kind of thing. Have you got a complex job, but your data is quite simple? I mean, here in biology, we talk about big data a lot. Biology data isn't typically that big. It's medium at best, and we can fit it quite easily onto terabyte-sized drives. But sometimes the computational job is quite complex, and molecular dynamics is probably a good example here, where the data files are not that large, but the calculations that need to be done require quite a lot of processing power. So there you want those multi-core processors, multi-processor machines. Have you actually just got a simple job, but you need to do it many, many times? And there's certainly examples of this in bioinformatics where you're doing a simple analysis, but you need to do it so many times that it becomes a very long job. You could split that out across different computers. You could split that out across different processors. If it's a simple job, though, you can, instead of using just one processor, if you've got two processors, then you can run two jobs at the same time. You're not really parallelizing your code, you're parallelizing your job. You could do the same possibly by just hiring another PhD student and getting them to run it on their machine while they're watching TV in the evening. You need to decide really what exactly is it that's holding up your research. What is it that makes you think you need higher performance computing? Is it time that's actually the key factor? Or is it a need for the convenience of doing it quicker? Are you on a deadline? Do you need to do it faster? Many laboratory protocols have 2-day protocols or weekend protocols only because people want to go home, not because the job takes 2 days. So if you speed up your data analysis or your computational job, how does that fit into your overall workflows? You think about that a little bit. I think, and this one's in brackets because it's perhaps more of the controversial comment, sometimes getting the resources you need can be slower than actually just starting now and getting on and doing it with whatever you can lay your hands on. Here, I've got monkeys on typewriters, but if you're going to have an argument with your IT department, purchase a machine that maybe needs to be custom built and bought from the States, and it's got 50 processors. If that takes you 50 days, you could have had your student doing one of those every day and have got the job done before the machine arrives. So that's a very perhaps cynical look at high performance computing or high throughput computing. But before you go and spend out the money and have the fight to get what you want, sometimes it is worth just sitting down and thinking, is that really what I need? Am I going to do this again in 3 months' time? What is the benefit of doing these things faster? If it isn't the fact that you can't actually do the job without the bigger machine. So the other thing you should be doing at that point is thinking about whether there are other people who can help you. Have you checked whether you've got local high-performance computing resources in your university or even company? Sometimes you do, sometimes you're not aware of it. Certainly in the case of Cranfield, I was in the life sciences department. We had all of this stuff for the engineers. No one else in my department really knew it existed. I went and found it, worked with them, and we did some work. But there's a chance, certainly if you're at a university, that you have access to something which maybe isn't immediately obvious to you. Go and check, go and speak to these people. They might be able to help you. But there is a significant chance, though, that if you don't know about it, it's probably not been bought for you or designed for you or set up for you. And so it won't be running the software that you need. I had a very, very helpful high-performance computing expert at the university who helped me do the things I need, and hopefully that would be the same for you. But this is really where working with people in projects like BioXcel are going to be an excellent resource for you. But go and have a check that you're not just missing something obvious local that you can use. And we're almost at the end of these slides. The alternative, of course, is to go and then look beyond what you've got to immediately access, and that's other resources such as cloud computing or national facilities or core facilities and other resources like that. Now, if you've got help with these, I think they're probably fantastic options. If you are starting out your group, going in a new direction, expanding your group, and you don't have the local expertise, then you will hear a lot about how fantastic and amazing and straightforward doing things in the cloud is. But I can tell you from personal experience, I find setting up things on Amazon a little bit confusing, and I kind of would like to think I know what I'm doing. So having someone who's done it before, someone you can talk to, this is still somewhere where there may be the option for the actual compute job at the end of the day, but you want to find that helpful person, the collaborator, who has maybe done it before that can help you out. I think it's not a route to try and go on your own from day one. So my final slide on this is really, I would say that the key challenge in choosing and getting hold of the compute resources for your team is not necessarily a computing challenge, it's a people challenge. It's understanding, from your point of view, the computers and your computational needs, thinking about what it is you really need to do and why you want to do it that way, so that you can communicate that need effectively to other people inside your organization or outside, to make sure that you can win those battles over purchasing, you can end up with the machine that you want, and that it does the task that you think you need to do. Most of the battle of acquiring that compute resource is going to be working with all the other people who can support you in actually getting it, setting it up, and using it. You're going to be doing the science at the end of the day, but the maintenance of the machine and then the support of that is going to be other people. And making the most of the resources you have, or that you do get, means having a team who know how to use it. And this almost goes back to my very first slide, where I said the first thing to do is think, if I want to do more technical computing, do I actually have the people who can do it, or can I get them trained, and can I support them in their learning and support them in their training as the team leader to be able to do the science? It's almost easy to buy the box and put it under the desk. You can then find that while it sits there using electricity, actually no one's using it properly. So that's kind of the end of a quick look at getting perhaps some more compute and choosing the compute. It's very much flavored by my own experiences. I labored the point maybe about struggling with IT departments. I had huge struggles with IT departments in my past. I have given this talk to a room full of real people, not a webinar, and I can't see you on this, but when I talk to a group of group leaders with this presentation, most of them were nodding in agreement that they've been fighting their IT departments too. So I think it's not a unique perspective. It's certainly something to think about. And don't dismiss your humble laptop for being able to do quite a lot of stuff that maybe you're looking to the high performance world when actually you can get quite a bit done with what you've already got. So I think with that we can end the formal part of the presentation and move on to the questions, if anyone has it.
Thank you very much, Lee, for that interesting presentation. So yes, as Lee says, we are open to your questions now, so feel free to type them into the questions box, and I will pass them on to Lee. I see there's one question in already from Comfort. I don't know, Comfort, are you able to, if you have a microphone, I will be able to open the microphone so that you can ask your question directly. I'm not quite sure I understood it from what you typed, so are you able to ask the question directly? Okay, yeah, okay, thanks. So the question was about the implication of internet junks in developing a compute resource. I was trying to understand what you meant by this. So do you mean, so your question is about something to do with the effect of the internet, but I'm afraid I haven't quite understood what you're getting at. Is it the, so maybe the question's about the sort of the relative performance of being able to access things online compared with locally. Maybe Lee, you could have a go at answering that question, and if that's not what you're getting at, Comfort, maybe you could follow up.
Have a go, I guess. I mean, there's two issues maybe with remote access to things. One being remote access to sources of data, which can be quite problematic. With the example I gave somewhere back in the slides of having to access maybe tens or hundreds of gigabytes to even terabytes of data sometimes, then your internet connection is going to be a huge limiting factor. Whether that's you downloading data to do something with locally, or you having local data that you need to upload to an HPC facility elsewhere if you're using one. That's a problem which is not easily solved. You're probably faced with whatever bandwidth you're faced with. Some places will enable you to, mail off hard drives or DVDs, and they'll put the stuff on their system for you, which isn't ideal. The other thing which perhaps is a limiting factor to do with the internet and bandwidth is your ability to sort of log on and use a remote system. And in many cases, when you're doing stuff with high performance computing and working with a remote system, you're going to be using a command line interface. And I would suggest that in most cases, even the most minimal bandwidth is going to be sufficient to log on to a terminal shell on an HPC somewhere and launch a job. I think from that point of view, location and bandwidth is almost irrelevant these days. I don't know if that answers your question.
Thank you very much, Lee. So hopefully, Comfort, that answers your question. Please feel free to post a follow-up if that wasn't quite what you were getting at. I don't have any other questions in the queue at the moment, so while people are thinking of something that they might want to ask, I'll make a couple of comments myself. So the first thing I was going to pick up on, Lee, was when you were talking about the procurement of machines and getting the idea across to your IT department that you want something a bit different. I was going to comment from my experience. I wondered whether you agreed or not. The one thing I found was that people were, if you could specify your requirements specifically in terms of what your needs were, then they were more open to making unusual choices rather than just saying, I need this particular machine. If you could say, well, I need a machine with more than 8 processing cores because I can run a program in parallel and I need this performance, then do you think that helps in the argument to the IT department, or is that just
I think that's probably a fair point, and I perhaps should have said that. I mean, your biggest challenge is going to be if you go to the IT department and say, I want this HP machine, and they turn to you immediately and say, we only buy Dell. And that's a real sort of conversation stopper. But if you go to them and say, I need a machine that has X amount of RAM and 2 hard disks and a certain processor, and here I found it as an HP machine, but it's an example, then they're more willing to go and have a look to see if there's a Dell that matches the spec. And so that probably is an advantage to be able to set out what you want. There will be times when there is nothing in their catalog that meets your needs, and then you've got to make a stronger argument. And perhaps also be willing to compromise. If you've picked something that has 24 gig of RAM and they can only get you one with 20 gig or something, then go back and think, is that going to do the job? Because it might be easier just to get that one. But yeah, being able to specify what you want is a good start point.
Yep. And I did have one other comment. I don't want to hog the floor, so if other people do have questions, do please come in. But it was a comment on your slides about the choice of platform. I would agree on the kind of point that a lot about the choice of platform is familiarity, and in terms of sort of tool for the job, can it if you've got something that works, that's good enough. Well, I would have one comment though, that if you are sort of scaling up and thinking about using higher performance systems in the future, it's likely that they are going to be Linux based or Unix based. So do you think there is some advantage in sort of gaining expertise in those areas by using that kind of system?
I think part of the, I guess my recent conversion back, shall we say, to Windows has been because of the availability of the new Linux subsystem for Windows, which, for those on here who may not be familiar or have heard of it, came out kind of last year, and it's a full Ubuntu distribution sat underneath Windows, which interacts with the Windows file system and everything quite well. So in that regard, Windows is now very similar to Mac OS in that you've got a nice, shiny, familiar user interface, but you can drop to a Linux-based or Unix-based shell very easily. So I think you can gain experience now and follow training you might find online about how to use a Linux command line on Windows just as easily as you would do on the other platforms now, but still be within your familiar environment. I think that's a little bit of an unmarketed benefit of Windows at the moment, certainly in the bioinformatics world, where everybody goes with Macs for that reason. But it could be a bit of a Windows ace card if they marketed it better.
Yeah, well, that's interesting to hear about that. Thank you. Okay, do we have any other questions from the floor just now? Please feel free to ask. No such thing as a silly question. If not, then I would point out that when these videos go online, there will be links to our online forums at ask.bioexcel.eu, so you can always ask any follow-up questions. Indeed, if you're watching the recording, you can post your questions there, and somebody in the BioExcel team will address them and get back to you. So if we don't have any other questions from the floor, then I think all that remains for me to do is to thank Lee very much for his presentation today, and to remind you again that there is a follow-up webinar on cloud and high throughput computing that will run at the same time next week, so you'd be very welcome to register and to join us for that as well. Okay, thank you all very much for joining us today, and I hope you found that interesting. Do check out what we have to offer at bioexcel.eu, and I'll hopefully see you next week. Thanks very much, everyone.